Good morning. Our names are Carlos Ardila, Pablo Ruiz, Juan Hernandez, Juan Diaz, and Oscar Clavijo, and me, Maria Cortez. And today we're presenting what we did for the Infirm's student team competition. This is the outline of our presentation. First, we're going to talk briefly about the problem definition. Then we're going to present the methodology that we used to solve the problem. Then we're going to present our results, and finally, our main findings and conclusions. So we'll first start with the problem definition. The objective of this problem was to determine a fully invested equity portfolio consisting in long positions for principal global investors to minimize the trade-off between risk and expected excess reward. The time horizon for this problem was a 10-year term starting the 3rd of January of 2007, and this problem included additional extensions to the Markowitz mean variance optimization framework. These extensions were, in first place, that the number of assets was limited to a predefined range between 50 and 70 assets. Also, we have a constraint in how much our portfolio could closely follow the market in terms of the weights and the risk of the assets. And finally, we couldn't ignore the transaction costs that are generated when we rebalance our portfolio. Therefore, we had to find a way to include this cost in our implementation. It is worth mentioning that the resulting problem cannot be solved with a convex optimization approach because it has a nonlinear objective function and nonlinear constraints. Therefore, we had to search for different approaches to solve the problem. Now I am going to present the methodology that we used. So we did an extensive literature review, and we based our work in an article written by Di Tolo and Rowley in 2016. They had a portfolio selection problem, and they divided this problem in two parts using a master-slave approach. First, they had a master problem that consisted in a meta heuristic to determine the assets to include in the portfolio, and then they had a slave problem to determine the weights of these selected assets. We did a similar approach. We first had a master problem that decided the assets to include in the portfolio. We did this with a genetic algorithm, and then we created a slave problem to determine the weights of the assets using an exact approach, specifically a mixed integer nonlinear program. This is a summary of our methodology. So for each rebalance date, we had around 500 assets, and then the genetic algorithm selected between 50 and 70 assets, and finally, the nonlinear solver selected the weights of these assets. As mentioned before, the master problem consists in a genetic algorithm. Genetic algorithms are heuristics based on biological evolution. And the idea of these algorithms is to move from an initial population of solutions to a new population of solutions using operators based on natural selection, for example, crossover and mutation. So the algorithm works in the following way. First, we have an initial population of solutions. Each point represents a portfolio with a specific risk and a specific return. And then the algorithm selects the best solutions or the best portfolios. These are the ones that have less risk and more return. And then the algorithm makes combinations between these best solutions to create new solutions. The algorithm continues iterating, therefore it will select again the best solutions and combine them to create new solutions. The algorithm continues iterating between these last two steps until a stop criterion is met. After the assets were selected with the genetic algorithm, we did a slave problem, and the objective was to determine the weights of the assets that were previously selected by the genetic algorithm. So for implementing this slave problem, we created a new set that was not included in the problem statement. This set consists in E indexed in T, that are the assets that were selected by the genetic algorithm for the rebalance date T. As a baseline case, we used a risk aversion parameter lambda equal to 0.1. However, we then tried with different values of lambda to see how our model changed with different risk aversion levels. These are the variables for the slave problem for a single rebalance date. First, we have a variable for the decision of how much weight to assign to each asset. Then we have another variable for the decision of whether or not including an asset in the portfolio. And we also have a variable for the turnover of each asset. This is the absolute value of the difference of an asset's weight between two consecutive rebalance dates. The number of variables of each of these types is the number of assets selected by the genetic algorithm. Therefore, selecting previously the assets to include greatly reduces the variables of this exact approach. This is the objective function of the problem. As mentioned before, it's minimizing the trade-off between risk and expected excess return. However, we added an additional term, this term, to include the turnover. So the problem statement said that 100% in portfolio turnover reduced the portfolio return in 0.5%. Therefore, we added a term that is 0.5% multiplied by the aggregate turnover. In terms of the programming language, for the master problem, we used R. We used R because it's an open source tool and also because it has many packages that perform a wide range of tasks. For example, it has a package that we used that is called GA that has functions for optimization using genetic algorithms. Therefore, it was very useful for our implementation. Also, this package allows us to parallelize the genetic algorithm, and so it can find a good solution in less time. We connected then R with Julia, because in Julia we implemented the slave problem. We selected Julia because it has a modeling language for optimization that is called JUMP, and the code is the same for any solver used, whether commercial or non-commercial. Therefore, changing the solver is really easy, and in this case particularly we used the solver von Min because it solves mixed integer nonlinear programs.
Okay, once the solution methodology was clearly selected and defined, it was implemented on the model. We performed several portfolios, changing between them, the rebalancing period, and the lambda risk aversion. The following plot shows most of the portfolios that were performed, and each point represents a portfolio. The plot's conventions the following. Each portfolio has a letter that can be M, B, Q, or S. It represents the rebalancing period that we decide for each portfolio. And next to the letter is the lambda value of the risk aversion. As you can see, the green point that corresponds to a portfolio that is rebalanced every 2 months and has a lambda aversion of 0.2 was the most efficient portfolio we performed. It dominates clearly most of the portfolios, and because it is has a higher return with a lower risk, and to decide it between quarterly with 0.2, it was by the Sharpe ratio that was higher from the green portfolio. So we couldn't perform a portfolio that has an annualized return of 6.89% with a risk of 3.03%. Now, comparing it with the market, we can easily see that our portfolio is placed between fixed income 10-year maturity portfolio and the Standard & Poor's index. Two important considerations have to be talked in this point. First one, we cannot conclude if our portfolio is dominated or not by an efficient frontier of the market. Imagine you can draw an efficient frontier that could pass throughout our point, so it will be as efficient as the market, or maybe it could be dominated by an efficient frontier that is above our portfolio. The second consideration is that maybe is not as well as efficient to compare our portfolio with the Standard & Poor's index because of the transactional cost that we are considering in our portfolio, but in the index is just a reference, or it is not considered that item. Those are the main performance metrics for our portfolio. The first three: the cumulative return, the annualized return, and the Sharpe ratio that measures the portfolio's profitability. So we've got for a 10-year time horizon a cumulative return of 94.71%, therefore an annualized return of 6.89%, and a Sharpe ratio or a 31.26. The last three items: the information radio, the analyzed tracking error, And the analyzed excess return measures the difference between our portfolio and the benchmark. As we have a highly conservative and a high restricted portfolio, it was expected that our results were not as profitable than the market. In addition, we performed a sensitivity analysis in order to analyze how we're affecting the additional constraints to the traditional problem to our model. This point is the original portfolio we gave in the last slides, and the rest of the 3 points are the portfolios that we run without taking into account the associated constraint. You can see that the red point is pointing the main conclusion of this sensitivity analysis. When we did not take into account the tracking error, we've got a portfolio that dominates the rest of the tree in terms of because it has an annualized return that is higher and a lower risk. So if we could relax or even eliminating that restriction, we could have very good results that we'd have.
As for the computational cost of our algorithm, it was below before the maximum time allowed for the methodology to run. The average time was 2.38 minutes, and from this time, the most of it took the genetic algorithm with 1.84 minutes. Finally, the Julia code took about 30 seconds to run. So just probably we had a lot of solutions, a lot of portfolios, and we needed a way to analyze all this information. For that, we'll build a Shiny web application using R. Now I'm going to show you a short demo of this tool. First, we select a portfolio, in this case by monthly with lambda 0. Here you see the turnover for each of the months of the portfolio. You can also see the returns of each balancing period. You can see the returns, turnover cost, and the adjusted returns for each rebalancing period. Also, for each portfolio, you can see the overall metrics that each one has. For the case of bi-monthly with lambda 0, we have a Sharpe ratio of 14.34. Also, you can see and analyze the behavior of each company in the portfolio. We have the company, and we can add any metrics and statistics that are relevant to you. Finally, we use a Stingray Visualization in which each line is a company, and the width of the line is the weight that has that company in the portfolio during that month. So we can see how a company has behaved in the whole of the portfolio. You can change the time horizon in order to see how a company has behaved. And then we can change to any of the solutions that we run. As conclusions, our master-slave approach allows us to reduce the problem size and reduce computational cost. The genetic algorithm allows us to have a very scalable solution. That means that can be applied to bigger indexes. Finally, the technology we use for the Julia allows us to have, for example, if a new solver comes out in the market and is better than the new ones, we can change the parameter and install the new solver. In the financial results, the resulting result is highly conservative. That means that it also have a lower return than the market, but also that means that during the better periods of the market, it also have lower exposition to the risk. Finally, we believe that relaxing the tracking error constraint could increase profitability and reduce risk of the solutions. Thank you.